Hi everyone. In this video, I'm going to go over an application of Newton's laws. So in this example, a 19.5 kilogram curling rock is thrown along the ice and experiences a force of friction of 9.2 newtons backwards. In part A, we want to find the other forces acting on the rock, and in part B, we want to draw a free body diagram and find the net force acting on the rock. So I'm going to start by drawing a free body diagram, just so we can see what's going on in this situation. Okay, so from the problem, we know there's going to be a force of friction acting in the backwards direction. Right, and we know the force of friction is 9.2 newtons. Now, if we assume that the forward direction is positive, then the backwards direction will be negative here. So I'm going to put a negative sign in front. We also know that there's going to be a force of gravity acting on this rock, pulling the rock down. And we know the force of gravity is equal to the mass times the acceleration due to gravity. Okay, the mass of the rock is 19.5 kilograms. The acceleration due to gravity is 9.8. So when we multiply that together, we get 191 newtons for the force of gravity. There's also going to be a normal force, right? Since this curling rock is on the ground, there's going to be a normal force acting in the upwards direction. And the normal force is also going to be 191 newtons, right? It's going to be the same as the force of gravity. And here, if we assume up to be the positive direction, then down would have to be the negative direction. So we'll put a negative in front of the force of gravity there. And again, the reason we have the negative there is just because we're assuming up and forward is the positive direction. Right? So the opposite directions have to be negative. Okay, and the question also asks us to find the net force. So the net force here, right? The net force we can find by just adding all the forces up. So here we can see that the normal force and the force of gravity, they're the same. So these forces will cancel each other out. Right? And then we'll just be left with the force of friction. So the net force is just going to be equal to 9.2 newtons, negative 9.2 newtons in the forward direction. Right? Because the only force that contributes to the net force here is going to be the force of friction. Part C, what's the average acceleration of the rock? Well, we know from Newton's second law that the net force is equal to mass times acceleration. So if we rearrange this, we can see that the acceleration is equal to the net force divided by the mass. The net force we know is going to be negative 9.2 newtons from part B. We know the mass is 19.5 kilograms. So if we divide that, we get negative 0.472 meters per second squared. So that's the average acceleration of the block. And here, the negative acceleration, all that means is that the rock is slowing down. Right? The acceleration is acting in the backwards direction. Part D. If the rock comes to a complete stop in 6.8 seconds, what is the rock's change in velocity? Well, remember, acceleration is equal to the change in velocity over the change in time. So if we rearrange this, we can see the change in velocity is just the acceleration times the time. And we know the acceleration, we just found it, is negative 0.472 meters per second squared. And we know the time is 6.8 seconds. So if you just plug that in, multiply that together, then we get negative 3.21 meters per second. So what this tells us is that the velocity is changing by 3.21 meters per second. Right? Or in other words, the velocity is slowing down, right? Because of the negative sign. The velocity is slowing down by 3.21 meters per second. Okay, part E. What's the rock's average velocity? To find the average velocity here, the average velocity is just going to be the arithmetic mean of the initial velocity and the final velocity. And the reason this works is because we know the acceleration here in this situation is going to be constant, right? This is a uniform acceleration problem. So we can use this formula for the average velocity. Okay, the initial velocity. Well, we know from part D, the change in velocity is 3.21 meters per second. Right, until the curling rock comes to a stop. So that tells us the initial velocity has to be 3.21 meters per second. And we know the final velocity when the rock comes to a stop, well, it's not going to be moving when it comes to a stop. So the final velocity is going to be 0. And if we plug this into our calculator, we get 1.605 meters per second. Okay, last part, part F. What is the change in position of the rock from the moment of release by the curler to when it stops? So again, let's look at what we're given here. What information are we given? So we know the initial velocity already is 3.21 meters per second. We know the final velocity when it stops is going to be 0 meters per second. We know the time is 6.8 seconds. And we're trying to find the change in position, right? The distance the rock travels. So here, I can use the acceleration independent formula to find my displacement. And the acceleration independent formula tells us this. So if you just plug everything in, right? I know my initial velocity is 3.21. My final velocity is 0. My time is 6.8 seconds. So if we just plug this all in, we get 10.9 meters. So this tells us that the rock will move forward 10.9 meters until it comes to a stop.